Hi everybody, welcome to our last lecture on planetary motion, where I want to discuss Kepler's laws of planetary motion and a little history in this whole thing. Um, One of the original ideas of how the planets moved around in relationship to each other was something called the geocentric theory. The word geo meaning earth and centric meaning centered. In other words, it was the idea that the Earth was the center of not only our solar system, but the entire universe, and the entire universe simply revolved around the Earth. Now, the person who's given credit for this is a Greek named Claudius Ptolemy, and he's largely given credit because he was the one who sort of wrote it down and published it. The geocentric theory goes back a long time before him, all the way back to the time of Plato, but he gets kind of all the credit for actually publishing the theory. And for the next 1500 plus years after he published this theory, it was the accepted idea. Not only accepted as far as science, but it was very heavily accepted in religious indoctrination. Until somebody came up with a different idea called the heliocentric theory. Helio meaning sun. And that was that our solar system was rotating around the sun itself. And that was the fixed point, and the Earth and everything went around the sun. And this was brought up by a guy named Nicholas Copernicus. Now, why did Copernicus not agree with Ptolemy? Why did he want to go out on and be different? Well, because there were some real problems with Ptolemy's geocentric theory. And let's sort of look at that in terms of some simulations here. You see, according to Ptolemy's geocentric theory, if we were to watch Mars, well, Ptolemy said that because the Earth was the center of the universe and the sun clearly went around the Earth, that was just fine. But the way that Mars appeared to move is that Mars appears to go forward, like it is right now, and then will suddenly seem to turn around and move backwards. In other words, back up into the sky and then go forward again. Now, Ptolemy explained this in something called epicycles. He said that planets, as they went around the Earth, did these little loops along the way. And that was just sort of the natural way things happen. Although it seemed really strange, the idea of a planet sort of being able to suddenly stop, move backwards, and then move forward again. But again, nobody really questioned that. Well, Copernicus realized that there was no way that could be possible. It just didn't seem to work. And what he realized is that what Ptolemy thought were epicycles is something we call retrograde motion. Now here's what's really happening. Keep in mind, remember we talked about orbital velocity. The further you are from something, the slower you will orbit. So that means that the Earth orbits the sun at a much faster rate than Mars orbits the sun. So what happens is, as the Earth is coming around, it sees Mars moving forward with it. But now, because the Earth is moving faster, where we view, we suddenly see it appears that Mars is backing up. But that's not true. It's just we're running past Mars. And so that gives the appearance that Mars has suddenly backed up into the sky. Now, it begins to move forward again as it moves along with us. So Copernicus realized that this was more likely the situation, that there were no epicycles, and that in fact the reason we saw Mars in this particular motion is because everything was going around the sun, the heliocentric theory. Now Copernicus was actually bothered by his own theory, and in fact when he finally published it, he died about 2 months I think later, which was actually fortunate for him because anybody caught teaching the Copernican theory at the time, this was sort of during the Holy Inquisition, was often tried and arrested and even killed as a heretic for going against the geocentric theory, which is what the church accepted. Galileo himself was not actually arrested and excommunicated for teaching the Copernican theory. It was another incident. But he was forced to stand in public and try to renounce the Copernican theory, even though he truly believed it was the right one. Anyway, so finally, after it really blossomed and the Renaissance came along, people really began to understand that Copernicus was right, the heliocentric theory was right. More and more people started studying astronomy for what it was. And along this way came a guy named Johannes Kepler. And he ended up working with a Danish guy named Tycho Brahe. And together they really advanced a lot of the way astronomy worked. And so Kepler came up with 3 laws around planetary motion. The first one is called the law of elliptical orbits. Kepler says that all planets will travel in elliptical orbits with the Sun at one focal point. Now, what does that mean? Well, contrary to what had been believed, even by Copernicus a bit, everybody believed that the orbits of planets were perfect circles because they believed the heavens was a perfect area. But what Kepler realized, and Newton also later confirmed, is that that really couldn't work that way. That in reality, you have a star, like our Sun, that is located at a certain point in space. And a planet like the Earth actually orbits in an elliptical manner. Now, an ellipse is kind of like an oval, so it has what's called 2 focal points. One right here and then sort of one out here in space that doesn't really mean much of anything. Now, I've exaggerated this elliptical orbit. It's not quite this elliptical, but just for exaggeration. Now, again, if you consider that idea of what we talked about with orbital velocity, what that means is when the planet is way out here, it's actually traveling its slowest. And when it's here, it's actually going to be moving its fastest. Okay? Those locations actually have very specific names. Closest to the Sun is called perihelion. That's the point when you're located closest to the Sun. Furthest from the Sun is called aphelion. That's when you're farthest from the Sun. Contrary to popular belief, when we hit perihelion, that is somewhere around January. Okay, now most people think, well, wait, shouldn't that be in the summer? No, the seasons have nothing to do with how close we are to the Sun. Just a quick astronomy lesson. The way the seasons actually work is because the Earth is tilted. So in January, when it is winter for those of us in the northern hemisphere, it's because the northern hemisphere is tilted away from the Sun. So most of the Sun's light hits the southern hemisphere, warming it. Now over here on around July or so, okay, when we're on the other side with our tilt, well, now the Sun's rays mostly bathe the northern hemisphere. Okay, so the seasons have to do with the tilt of the Sun, not how close we are to the Sun. So that's Kepler's first law. All planets travel in elliptical orbits, not circular orbits. Let's look at a simulation of Kepler's first law. So here you can see Kepler's first law of planetary motion in action. Again, this planet, I think this is Mercury, going around the Sun. Again, the Sun is here. The actual center, if it was a circular orbit, would be here. But this is a focal point of the ellipse, and this is a focal point of the ellipse. And you can actually see Mercury kind of speeds up as it approaches perihelion and slows down as it reaches aphelion. Kepler's second law, called the law of equal areas. This is a little bit of a confusing one when you hear it written out. It says this: a line drawn from the Sun to a planet in orbit will sweep out in equal area and in equal time frame. Now, what does that mean? Well, what Kepler was saying is that if I had a planet located right here in its orbit around the Sun, and I drew a line from the Sun to that planet, and then I wait a certain amount of time, well, because the planet is close to the Sun, it's going to move fast, and maybe after my time it gets to here. And now what it means is that this line here has carved out a certain area. Okay, I'll just call it A1. Now, if I wait for my planet to be somewhere else, let's say right here, and I draw my line again, and now I wait that exact same amount of time, well, it's farther away, so it's moving slower, so it may not get as far as along the arc, but again, if I draw this line and I carve out this area here, those areas are equal. Now you might think, well, what's the big deal? Well, one, it does help to verify both the elliptical orbit and the fact that the speed changes based on that distance. And then it also has something to do with a law called conservation of angular momentum, something that's a little bigger in rotational mechanics. To give you a better look at that, let's look at another sort of simulation. Now, here in Kepler's second law, again, we have Mercury going around the Sun. Now, if we start sweeping a certain area, and we sweep another area, okay, notice that the time frames are going to be the same. And each time frame that's measured out carves out a certain area. Okay? So each one of these areas are the same, okay, because distance and velocity are both changing. Okay? So as you can kind of see here, every one of those little colored areas are exactly the same, okay, as it goes around. And again, that has to do with, first of all, the first law, the idea of elliptical orbits, and then the way orbital velocity actually works. So that's basically Kepler's second law of planetary motion. Planet in orbit sweeps out equal areas in equal time frames. Kepler's third law, called the law of harmony, I'm not sure where I found that out, but apparently that's what it's called, is Kepler's way of determining what's called the period of an orbit. Now, period means time. In other words, the time to go once around. So, for example, the period of the Earth's orbit is 365 days. So how much time it takes to go around? Well, first of all, we're going to sort of base this on the idea that we're going to assume that the planet travels at a roughly constant velocity, because it is a set time throughout the entire year. And because it's going to travel at, we're going to say, a set constant velocity, orbital velocity, well, then that has to do with how much time it's going to take. So the way we get the period, t, capital T for period, we take 2 pi r, better known as the circumference of the orbit, and we simply divide it by its orbital velocity. So again, the way that works though, the fact that period is 2 pi r over your orbital velocity, again has to do with the importance of distance, okay, r. Obviously something that's very close to the planet will have a much shorter time period than, say, something that is much farther away, because it's traveling a longer distance and also at a lower velocity, it will have a much greater orbital period. So let's look at an example. So what we've got here is an example we did back when we were talking about planetary motion and orbital velocity, and that was a satellite orbiting 800 kilometers above the surface of the Earth. Now, two things we had established. One is that the actual distance r was 7.18 times 10 to the 6 meters, because we had to take the radius of the Earth and add on to it 800,000 meters. Then when we calculated orbital velocity, we found out it had a speed of about 7,453 meters per second. So now let's get the period of its orbit. Period, 2 pi r over the orbital velocity, 2 pi times that total r, 7.18, times 10 to the 6th, all divided by the orbital velocity of 7,453 meters per second, which gives an orbital period of 6,053, and that's going to be in seconds, okay, because standard units, right? That's in seconds. Now, that works out to be, if you were to do some dimensional analysis, the fact that 1 hour is 3,600 seconds, or 60 by 60. That actually means that this satellite takes about 1.68 hours, okay, almost an hour and 45 minutes, in order just to orbit the Earth once, okay, which is moving pretty fast. Okay, so that is Kepler's laws of planetary motion. First law, law of elliptical orbits. All planets travel in elliptical orbits with the Sun at one focal point. Second law, law of equal areas. A planet in orbit around the Sun will sweep out an equal area in an equal time frame. And the third law, the law of harmony, basically a way of calculating the orbital period of an object. The orbital period being the circumference divided by its orbital velocity. See you next time.